Okay, so we were looking at eigenvalue problems. So omega in Rn, bounded open set, and gamma equals d omega, and we were looking at minus Laplacian w u equals lambda u in omega, and u equal to 0 on gamma, and of course u not equal to 0 identically. This is the eigenvalue problem. So then we saw that there is omega n orthonormal basis of L2 of omega, also of H10 omega with some factor in the front, orthonormal L2 of omega of eigenfunctions, and 0 less than lambda 1 less than or equal to lambda 2 less than or equal to etc. less than or equal to lambda n tending to infinity of eigenvalues. So minus Laplacian Wn equals lambda n Wn in omega. So and omega n belongs to H10 of omega. Okay. So and we repeat these values according to the geometric multiplicity, the dimension of the eigenspace. So if lambda 2 is has a two-dimensional eigenspace, then lambda 2 and lambda 3 will be called will be the same. Okay, so then we proved the following theorem, variational characterization. We had the Rayleigh quotient R of V is integral of mod omega grad V square dx by integral on omega mod V square dx for V not equal to 0. And then we had the following theorem, that m positive integer. So Vm is the span of V1 to Vm, and V of 0 is singleton 0, and then we have that lambda m equals R of W1 W2 Wn. Okay, R of Wm equals max R of V not equal to 0, V in Vm equals min of R of V not equal to 0, V orthogonal to V m minus 1, and then finally this was also equal to min of all W contained in H10 of omega, dimension W equals m of the max V not equal to 0, V in W of R of V. So this was the min max or the intrinsic characterization. So this was the theorem which we proved last time. Okay. Okay, so there was some errata which I want to say. Errata is that integral W grad Wi grad Wj on omega is equal to 0 if I is not equal to j, integral on omega Wi Wj equal to 0 also if I not equal to j. This we already know. And then when I equals j, I did not write it very correctly, so this was integral mod grad Wi square equals lambda I, and then integral of course mod Wi square equal to 1. Okay, so this here I wrote integral grad Wi square or something like that. So there was something wrong here, and therefore now state and prove a similar theorem for the eigenvalues of a n by n symmetric real matrix. So you know that for a symmetric real matrix, the eigenvalues are all real. So you can write them in ascending or in order, ascending order for lambda 1 to lambda n, and of course the eigenvalues will be orthogonal in the usual sense in Euclidean space, and therefore you can state and prove exactly the same kind of theorem which you have. So we had also that lambda 1, which was the min of V not equal to 0, V in H1 0 of omega of R of V, we saw this. Similarly, for a matrix, you will have lambda 1 will be min of AVV by norm mod B square, V not equal to 0, and lambda n will be the maximum in this case here AVV by mod B square, V not equal to 0. Okay. So, this is the corresponding result you have for eigenvalue, and this is very useful in computing the eigenvalues of symmetric matrices. Okay. So, let us now continue with the Dirichlet problem. So, we have the following lemma. Let W belong to H1 0 of omega, W not equal to 0, such that R of W equals lambda 1. Then W is an eigenfunction for lambda. Okay. So, proof. So, this happens only because we are in the minimum, not because lambda 1 is the minimum of R of V. Then in that case, for the other higher ones, this is no longer true, and this is true because we are in the minimum. So, let V in H1 0 omega arbitrary, and let T belong to R. Okay, T greater than 0 for. Let us take T greater than 0. Okay. Then W plus TB is in H1 0 of omega, and you have, so you have R of W plus TB will be greater than or equal to lambda 1, which is because it is a minimum, which is equal to R of W. So, now that means integral grad of W plus TB dot grad of W plus TB by integral W plus TB square is greater or equal to lambda 1, which is equal to integral grad W grad W. So, without loss of generality, I will take integral W square equal to 1. I can normalize W. Okay. So, we expand and cross multiply and simplify. So, you get T square integral on omega grad V dot grad V plus 2T integral on omega grad W grad V plus integral grad W is greater or equal to lambda 1 integral W square plus 2T integral WV plus T square integral V square. But grad W equals lambda 1 W square. So, these two terms will get cancelled. So, divide by 2T and let T tend to 0. So, if you do that, then you will get integral grad W grad V on omega is greater than or equal to lambda times integral lambda 1 times WV for every V in H1 0 of omega. Apply to minus V as well, and that will imply you get the opposite inequality. So, you will get integral grad W grad V equals lambda 1 integral WV for every V in H1 0 of omega, and therefore, it is an eigen function because it satisfies the weak formulation of the eigenvalue problem. Okay. So, now we have a very nice theorem. Omega in Rn bounded open connected set, then lambda 1 is a simple eigenvalue, that is dimension of V1 equals 1. Any eigenfunction of lambda 1 does not change sign in omega. In particular, we can always choose W1 to be strictly positive in omega. So, this is a very nice theorem. It says that the first eigenfunction corresponding to the first eigenvalue is always of constant sign, and in fact it is strictly you can choose it strictly positive or strictly negative in omega. We can, so W or minus W1, okay, and okay, so this is what we want to prove. So, proof. So, let W be any eigenfunction corresponding to lambda 1, okay. Then W plus W minus belong to H10 of omega. We have seen this before, okay. So, now if you choose V equals W plus or W minus in weak formulation, so here grad W plus or grad W minus, then we know how to evaluate this. We have done this before. So, easy to see that R of W plus equals R of W minus equals lambda 1. So, this implies that W plus W minus are also eigenfunctions. So, minus Laplacian W plus equals lambda 1 W plus, which is greater or equal to 0, and therefore, by the strong maximum principle, we have W plus is strictly positive, or W plus is identically 0 in omega. Similarly, W minus is strictly positive, or W minus is identically 0 in omega. But both W plus and W minus cannot be simultaneously non-zero. Because they are the positive and negative parts of the W, and therefore they cannot be simultaneously non-zero, okay. So, therefore, you have that W plus is identically 0 or W minus identically 0. And now, so you have that the eigenfunction does not change, and in fact you can have it strictly positive. Therefore, if two linearly independent eigenfunctions exist, they are orthogonal, then integral W1 W2 will not be equal to 0, okay. But we always know we can find orthogonal basis of eigenvectors, eigenfunctions, and therefore that will not be possible, because any two of them will always have constant sign. So, the integral cannot vanish, and therefore you have that lambda 1 is simple. So, this means what? So, you have that 0 less than lambda 1, which is strictly less than lambda 2, then of course we have lambda 3 and so on. So you have here, because of the strong maximum principle, so remark, also applicable to sigma aij du by dxj dv by dxi dx plus integral a naught uv dx equals lambda times lambda 1 times integral uv dx, okay, lambda, let us say, okay, the eigenvalue problem for the elliptic operator where aij satisfy ellipticity condition and a naught is greater or equal to 0. Okay. So, this theorem is, now we have applied the strong maximum principle. So, which we usually need, u should be so we needed that w should be in C2 omega intersection C of omega bar. But we already know that w belongs to C infinity of omega, this is known. Now what about C of omega bar? Well, if n is less than or equal to 3, by regularity w belongs to H2 of omega, which is of course contained in C0 of C of omega bar. Okay, but this for almost every simple domain. Okay, but if you want n greater than 3, then we need to assume more smoothness. So that if it's in W is in H2, therefore it will be in H4, if it's in H4, therefore it will be H8, etc. And that will need more smoothness of the boundary till you get sufficiently high so that you can bring it inside C of omega bar. Okay. So, remark, so we said that if you have minus Laplacian u equal to f and u equal to 0 on the boundary, then this is the displacement of a membrane. So if you have minus Laplacian u equals lambda u in omega, u equal to 0 on d omega, then this is nothing but vibration of a membrane. So lambda 1 is called the fundamental frequency, and lambda n are called the overtones. Okay, so if you have a drum, so a drum is, what is a drum? It's a membrane which is stretched over a frame, and then you beat this membrane, then you get so the vibration will be given by these this thing. And okay, so if you look at the n equals 1, omega equals 0, 1, of course here all the eigenvalues are simple, and you have u1 of x is sine pi x, which is of course strictly positive in 0, 1. Okay, theorem, monotonicity of the spectrum with respect to the domain. So let omega 1 and omega 2 be bounded domains in Rn, such that omega 1 is contained in omega 2. So, let lambda n omega I, n equals 1 to infinity, I equals 1 to be the eigenvalues of the Laplacian in omega I. Then for every n we have lambda n of omega 1 is greater than or equal to lambda n of omega 2. So, if your domain is bigger, the eigenvalues are correspondingly smaller. Each one, okay, has this inequality. So, proof is just very simple. So, if you have u is in h1 0 of omega 1, so this implies that u tilde is in h1 0 of omega 2, extension by 0. And further, integral on omega 1 of mod grad u square equals integral on omega 2 mod grad u tilde square dx, and integral on omega 1 of mod u square equals integral on omega 2 u tilde square. Therefore, Rayleigh quotient with respect to omega 1 of u is the same as the Rayleigh quotient with respect to omega 2 of u tilde. Now, result follows immediately from the min-max characterization. So, if W, dimension W equals n, W in h1 0 of omega 1, then W tilde is set of all u tilde u in W, then dimension of W tilde equals n, and W tilde is contained in h1 0 of omega 2. So, and the Rayleigh quotients are the same. So, the maximum over W is same as the maximum over W tilde, but there are more spaces in omega 2 which are of m dimension, therefore, the minimum of the maximum will be less for the bigger domain. Okay. So, it immediately follows from the characterization of the thing. Okay. So, now we saw that the first eigenfunction W1 does not change sign, omega connected. So, if j is greater or equal to 2, integral W1 Wj is 0. So, this implies that Wj must change sign. You cannot have something which is constant sign anywhere. So, we have a nodal line of an eigenfunction is a curve in omega other than gamma, such that the eigenfunction vanishes on it. A nodal domain of an eigenfunction is a subdomain of omega where the eigenfunction is of constant sign. So, I have omega here. So, suppose u vanishes along a curve like this, then u will be positive here, u will be negative here, u will be 0 here, u will be 0 on the boundary also, and these two are called nodal domains. You could also have nodal domains like this. So, u equal to 0 is a closed curve like this, then it could be positive here, it could be negative here, and so on. So, you could have many nodal domains. So, if you take in n equals 1, omega equals 0 1. So, if you take sine 2 pi x, then it will be like this, sine 3 pi x will be like this, and so on. So, you have, these are all nodal domains, this is a nodal domain, this is a nodal domain, and you have. So, now we have a very beautiful theorem. Let lambda k greater or equal to 2 be an eigenvalue such that lambda k is strictly less than lambda k plus 1. Then an eigenfunction u of lambda k has at most k nodal domains. So, if you look at the previous example, all the eigenvalues are distinct. So, W2 had this thing, this is sine 3 pi x. Okay. So, this has 3 nodal domains, this is exactly 2 nodal domains, and so on. So, in general we can say that you have only at most k nodal domains. Okay. So, proof. So, u eigenfunction for lambda k. So, let with L nodal domains. Omega I equals 1 to L. So, in each omega I we have minus Laplacian of u equals lambda k of u in omega I, and u equal to 0 on d of omega I. So, define ui equals integral u restricted to omega I in omega I, 0 in omega minus omega I bar. Then ui belongs to h10 of omega. Further, I not equal to j, omega I intersection omega j will be empty, and this implies that integral ui uj on omega equal to 0, and this implies that the ui are linearly independent. Therefore, V equals span u1 to ul, and dimension V is same as L. So, integral on omega I grad ui square is same as lambda k integral ui square. And therefore, this implies that integral on omega of mod grad ui square equals lambda k integral omega ui square also. And since all the omega i's are disjoint, so omega I is disjoint. So, this implies that R of V is also lambda k for every v in capital V. So now we are through. So dimension V equal to L, okay, and lambda k is less than equal is strictly less than lambda k plus 1, okay, and you have that the maximum of R of V equals lambda k, and therefore the dimension of V is L, and therefore this implies that lambda L has to be less than or equal to lambda k. And lambda k is k plus 1 is bigger than, and these two together imply, since we are writing in increasing order, that L has to be less than or equal to k, because lambda k plus 1 is strictly bigger than lambda k. So lambda L is less than or equal to lambda k, so L can be at best equal to k, and that proves the theorem. Okay. So that proves that at most k nodal domain. So remark, a slight modification of this proof using more sophisticated properties of eigenfunctions says that the hypothesis lambda k less than lambda k plus 1 not necessary. Therefore, for every k we have that eigenfunction of lambda k has at most k nodal domains. This is called the Courant nodal line theorem, and you can see this for instance in Courant and Hilbert. Volume 1, Methods of Mathematical Physics. Okay, so that is the title of the book. So Courant nodal line theorem. Okay, so for instance, if you take n equals 2 or k equals 2, since an eigenfunction of lambda 2 must change sign, there exists at least two nodal domains. But by Courant theorem, there exists at most two nodal domains, implies there exists exactly two nodal domains for every eigenfunction of lambda 2. So for lambda 1 there is exactly one nodal domain, for lambda 2 there are exactly two nodal domains. Not true for k greater equal to 3. For instance, in the square in 0 1 cross 0 1, we have lambda 2 equals lambda 3 equals 5 pi square. So eigenfunction of lambda 3 which is also equal to lambda 2 has only two nodal domains. So we just see that the min max has many applications. These are just some of the applications, and the spectrum of the Laplacian has several very interesting properties. It gives us a lot of geometric information about the domain, and it is a very fascinating subject, which is in the confluence of geometry, functional analysis, and partial differential equations. Okay.